The following content has been provided by RWTH Aachen University.
Good morning, everybody, and welcome back to our last lecture of DIS1 this semester. Before we dive into today's topic, which is going to be about the sort of continuation and finishing up of the 10 golden rules, we'll talk about briefly what we did last week. And I'll also have at the end a little bit of a lookout for where things are can be going for you next in our set of classes. So stay tuned for that for sure. Let's get started with the review of last time. We talked about the 10 golden rules of interface design. So we're just going to do a collection here and see if we can remember all of those and get them together somehow. I'll give you guys a chance. Anybody want to start with a few that they remember? You can tick off the easy ones. Aparna, yeah, sure, go ahead.
Speak the user's language. It's better not to use complicated engineering terms. Rather, if you just go and talk to the user and say, hey, how do you do this? Probably they'll explain in their own language and you can probably use those words, and that's better.
That's right. So the vocabulary, but also the concepts from the application domain. Sarah.
Yeah, another rule was to be consistent and predictable. So you don't use different fonts or sizes, and yeah.
Yeah, and that consistency goes super wide, right? Not just the visual things like fonts, but it's also, again, concepts, wording, the way that you spell things, the way that also you, for example, present commands. It's very weird if in one case I delete a file by opening a context menu, and then the next moment it's by the context menu isn't there anymore and I need to do some keyboard combination or something like that. Okay, so that's consistency and predictability. I'll just go down the list here. Jasper, go ahead.
Yeah, the next rule would be hire a designer to do it yourself. There's some people who can do it better than you.
That's right. Yeah. We're good at a lot of things, but not necessarily in visual interface design and visual aesthetics and so on. And it's just, it's in part it's a talent, in part it's a trained skill. And don't expect to have that automatically. There are people who do. I'm lucky enough to have some of those in my lab who combine being a great computer science student and having a good eye for design, but it's not a natural thing. So you want to get somebody who knows this stuff in and out and has practiced it for as long as you've been practicing to code and develop. Victor.
Reducing memory load or something like that. So we don't need to overwhelm user with a lot of knowledge in the head. So try to have some cues, signifiers, and so on. Yeah,
and also there are some things that people will need to or will want to remember from memory over the long term, like keyboard shortcuts. And it's helpful to give them access to those kinds of things very easily so they can remind themselves, so they don't need to always dig them out of memory if they've been away from the software for a while, for example. Tejaswini.
Yeah. So you address the diverse needs of different users. So across age range, they might expect different things from the interface. So you should be able to address all these needs, but without conflicting with the rule of keeping the interface simple. So
that's right. Very good. Yeah. So and diversity, I should maybe add to this from last time. Of course, goes way further than age. It's cross-cultural questions. For example, to this day, if you think about it, it's mildly weird that we're pushing around tiny yellow folders on the Windows desktop when those Manila folders, they're called, are something that everybody who works in an office in the US knows by heart because it's just a standard way of filing stuff. And you've probably never held one in your hand if you work in Germany, for example. They're just not what we do. So, but the metaphor was just used and carried over because the team back then, probably all American teams thought, oh well, that's obviously how everybody thinks about folders. And guess what? Outside the US, not a lot of people do. So it's a good example of how you can actually have a cultural bias in your interface and you don't even know that it's going on. And of course, this also applies to all the various ranges of abilities that people have. We haven't talked in detail about this, but the design for what people used to call, accessibility and special needs and so on, was always placing a focus on, oh, this person can't do that, or this person can't do this. And that's been changing in recent years, fortunately, as a perception that it's really more about universal design. That's the term where you will find this today. And the idea is that we're all disabled in some way all the time. All you need to do is put on a pair of gloves while you're biking and try to use your smartphone. You are effectively disabled, if you want, to use your smartphone touchscreen at that point. So these so-called disabilities are really a factor of your own innate abilities, your physical abilities, which can be, good or not so good in a particular area. Then the context that you're in, like wearing gloves, for example, has nothing to do with your innate abilities, of course, but it still, encumbers you. And then thirdly, the quality or suckiness of the interface technology in how far it adjusts to those particular innate abilities and context that you're in. So today when we talk about this, we use the term universal design to just make it clear that as far as I can see my system to be used with people of different innate abilities, people in different use contexts, I need to make sure that my technology covers those, so nobody is unnecessarily encumbered by it. All right, so that's diverse user needs. Sarah, you got another one?
Yeah, another one is about feedback. So especially giving useful feedback, not only giving feedback when the user presses a button or something, but also, for example, progress bars, which are linear and not showing, for example, 50% for 10 minutes and then 99% in the next minute, like that. So the user can really work with this feedback and rely on it.
Yes. And just to see the timeliness of that, progress bar thing, if anybody else caught the last season finale of Lower Decks, there is a progress bar finishing at 99% and stopping to a crawl right there in that animated series. So it's a topic even in the far future. So hold on to that thought of linear progress and progress bars. Good. And being responsive was something that was also in there. We'll talk about that a little bit more. But the 0.11 and 10-second rule are equally applicable. Okay. We're still missing a few, so including the first one, which kind of makes me a bit nervous. I hope you didn't forget about that.
I think the first one was keeping everything simple as possible.
That's right. Yeah, and that doesn't mean dumbing down an interface and making it hard to do things because we're missing features beyond what can be cut down, but keeping it as simple as the task and the context and the user allow, right? So that feature creep principle is a really dangerous thing that you can fall into when you start working on a project, especially for a longer time when feature requests keep piling up and you need to tackle that balance between feature richness and usability. So that's a challenging one. So we're still missing a few here. Sarah, you got one more?
Yeah, it's avoiding errors and if they happen to help recovering from them.
That's right. Yeah. So that is about just keeping the interface, keeping people out of error situations, because as I said, you can predict that they're going to be annoyed when that happens. And if you cannot avoid that, making sure that in that really stressful situation comparatively for the user, to get them out of that situation as quickly as possible with especially carefully designed dialogues and constructive feedback. Okay, so that's the errors, and undo was a topic that we also talked about in that context. And then we have, I think we got two more left. Bilit?
I'm not sure. I'm a little bit late, but did we talk about designing clear dialogues, like letting the user know where they are, what they can do? Yeah.
Actually, we did not mention that one yet. So designing, making sure people know where they are, what they can do here, and how they get back to where they were before. Those were those three questions that users often ask themselves when they're navigating a UI. Exactly. Mm-hmm. So clear exits on how do you get back to what users often consider a safe space, right? Like on a website, giving people a home button that takes them back to the home page of that company or website. That's something I'm sure you've used often enough when you were like lost in some deep down, submenu of a shopping site. Like, okay, and just get back to the starting page here. Okay, and then we got one left. Julia, go ahead.
I'm not sure whether I followed it correctly, but I think the graphic design is missing, right? So that we.
No, we did mention the graphic designers. That was actually that was mentioned earlier. So getting somebody who has the innate abilities to do visual design. We're missing another one, Victor.
If I'm not mistaken, we missed help in documentation. So we need to provide users some kind of onboarding, manuals, suggestions, and so on to facilitate the life, basically.
That's right. So making sure, and remember that was a whole continuum of different ways of providing help, right? From this quick like tooltip-like thing that is very easily accessible, gives you just a little snippet of information that might get you out of a pickle when you don't know what that button does again, all the way to the longish written or maybe even, God forbid, printed documentation that people can go through and read if they really need to smarten themselves up on a UI. Right on. Okay, so those were the 10 golden rules. Now, what we didn't cover, there's a little bit of an encore for the 10 golden rules, because there was one concept that we actually kind of skipped over last time, and it's a topic so dear to my heart, one of my pet peeves in user interfaces, that I want to make sure that we cover this. It has to do with this area of being consistent and predictable. You may remember we talked about the principle of least surprise, right? You design an interface in a way so that the user, if you have different options in your design, you design it in a way that it least surprises the user, because surprises are usually not what people are looking for in a UI. They want it to do the things that they expect it to do. And closely related to that is the issue of timeouts. And there's a very simple rule considering timeouts in user interfaces, and that is timeouts are always evil, right? They're never good. Here's this great example where I think we talked about this, right? The bar, we mentioned this earlier, where this is not just a design that messes with your expectations, but it also puts a timeout into a user interface, press the bar for 3 seconds and then wait for 15 seconds before it unlocks. That is completely unexpected, and this time will always, that's the problem with timeouts in general. Timeouts will always, when you put them into an interface, you code them into a UI, they will always either be too short or too long, because the mathematical probability is 0 that the timeout is exactly what the user needed at that time, right? Simply because it's an exact time of, let's say, 3 seconds here, and then, or 18 altogether, and the likelihood is 0 that that is exactly what people needed. So timeouts will usually either annoy you because they take too long, or they will annoy you because they expire before you had a chance to do something. Right? So don't do this. And I want to give you a couple more examples of timeouts and show you how prevalent they are in user interfaces, and just drive home the fact that timeouts are almost always a case of lazy implementation. Because a timeout is easy to build as a coder. You just put in a little loop and you count to X and you decide what X is, and then you act, because you're like, well, if the user didn't do anything until now, then I'm sure he meant this. So you're deriving meaning from the user just not doing something for a particular period of time, which is completely unfounded, right? Because real life doesn't work that way. So I'll show you an example. Station search. If you have a radio in your car, some of these have a function where you press a button. Let's say you move to a new area, or you're like in a new city, and you get different receptions. So you want to fill you want to listen to your favorite country radio station again, because you can't get your radio station that plays country music and you love country music. So you hit that station search button, and what happens then oftentimes is that it will find the next station, will play it for 5 seconds maybe, or 10 seconds, and then it will move on to the next one. And that way it will go through the entire band, cycle around, and play all the stations it can find, 10 seconds each. And you're supposed to press the button, some button, when the station comes up that you want to listen to. Now, people who designed this thought, oh, this is really smart from us, because that means that user doesn't need to take their hands off the wheel and keep pressing that next station button. They can just, keep going, and when the station comes up, they only need to reach over once and press it. But now imagine yourself in your fancy sports car, driving down, towards Kaiserplatz, coming, out from like Europaplatz or something, and so you're driving there, and you're supposed to take a pretty steep left turn, right, to make your way to the main station or something. And right at that moment, you're about to take that left turn, your country station comes up, because Station Search now found it. So it's going to play it for maybe 10 seconds. So you got two options, right? You can either ignore safety and your, care for your personal life, take one hand off the steering wheel and try to take that sharp turn with one hand and press that other button within those 10 seconds. Or you can decide, now I'm going to, stay alive and make that turn properly. But then that station has gone away, right? It's, the 10 seconds have passed, and your station search will go on with all the other stations it finds. And then you need to wait until it comes around next time. And guess what? By the time it does its second scan, it will probably play even more stations, because it now switches to that, DX mode, where it even plays like stations that were lower in their reception intensity the first time around. None of those decisions are good, right? If, on the other hand, you are in a hurry and you just want to find that station really quickly, then it's going to be really annoying to listen to all those other stations for 10 seconds each, right? So bad timeout, right? Not a good idea. I want to give you another example. I'm not sure here. Can you raise your hand? I just want to see if you guys remember this. This is writing on the T9 system. This was when we had to do multiple taps, right, on our dumb phones, I need to call them now. All right, lots of people know this stuff still. That's good. And do you remember how hard it is to write words like hi on this? And okay, so you can take down your hands. They don't time out anymore, by the way. They stay up, and all your reactions will, I think, now stay up until you take them down. What is the hard thing about writing hi on this T9 system? Remembering that it has to do with timeouts. Yeah, Tejasvini, go ahead.
So what would happen is that because H and I were located on the same button, so typing, you had to type it very fast in order to move from one letter to the other located on the same button. So sometimes what would happen is that after typing H and you wanted to type I, it would not come as a second letter. The first letter itself would get modified because the user's timeout didn't match with the system's one.
Precisely. So you had to first type, the letter, hit the key twice to get the H, and you have to do that within a particular timeout. Let's say it's like half a second or something, right? So that you advance on. And that's something we got used to. That was, annoying, but you could just, because you usually type faster than half a second per letter, right? We know that from our GOMS models and stuff. So that's not that hard to do. But then the real problem is when you want to type the H and then you have to wait until the timeout expires, and then you have to hit the key 3 times again in rapid succession to get the I. And even though it's just a half second, that's really short. I'm sure that's what the designers of this interface thought too, right? That's not a long time. But I know that some people actually went to very weird techniques just to avoid that little timeout. I know people who would hit GH, so they would hit letter 4 twice, then they would hit any other letter, any other key, then they would delete that other thing, and then they would hit GHI, just so that they could keep typing. Not even sure if it was faster in the end, but what it shows is that people are so annoyed by these short timeouts because they really make you almost like stumble in your walk when you're walking, right? They interrupt your interaction sequence in a very weird way, and it's very unnatural. It's an unnatural pacing of your interaction. And you're so much faster when you don't get those kinds of interrupts, right? So bad idea. And it's amazing to what kind of lengths people go to avoid timeouts. And then just a third one, Ollie, we should probably put a picture in on this one for next time too, but I think everybody knows it from heart. ever been to the Deutsche Bahn website and you've carefully entered all the details for the ticket you want to buy, and then they ask you for your credit card, and you have to run off and find your credit card, and it's in the other jacket that's in the other room, and you find it, and and then you come back to your computer, and when you get back and you type it all in, it actually still lets you type in that stuff in the field, and then when you hit submit, it says, oh no, you were too slow. You can start all over again because we decided to throw away all the information that you entered. So that's a really bad idea, right? That's another example of a timeout. And why is that timeout evil? Because it will, it will always hit you when you don't expect it, when you are a little too slow in your interaction. It will get you. So that means it will especially hit people who are in an unusual situation, right? It's not when you do your normal purchasing and everything goes smoothly, then you'd never notice these. But when you're in a situation where somebody calls you, or you're a person who is a little bit, unexperienced with using that technology, or has some kind of disability or whatever it might be, or you're doing this on a very slow connection or with a very bad UI that is hard to use on a small phone or something, that's when these things then kick in, and it's the worst time to do this, right? And they're just there because the Deutsche Bahn was somehow too lazy to implement something smarter, right? Because I understand that they at some point need to close open sessions for security reasons and for database cleanup reasons, but is it so hard to then at least say, you know what, we closed that session, you need to enter your password again, but if you do, we will take you back to where you were before you entered this, right? And leave that data in there, at least for a day or something, where we know that, okay, people are not going to leave that open for a day to complete a transaction. So this is a typical example. And timeouts are easy to implement, but let's be honest, it's chickening out as an implementer, right? It's chickening out as a developer because you're taking the easy way out and you're not thinking about a good interaction. This is also a great example of a universal law. Isaac Asimov's 3 laws of robotics, right? Every geek knows these. And similarly, you have sort of, a couple of laws for user interaction. And one of the prime directives, so to say, that we have in user interfaces is a system should never, ever lose the user's work progress. So whatever the user does, like if you enter, you write your thesis, and you're almost done, and then and Word decides it's going to throw away your file, you're not going to be happy, right? That's an extreme case. But throwing away what I entered as my, preferred connection as a train when I'm on the Deutsche Bahn website, throwing that away is also throwing away work that the user did. They picked, maybe carefully, a particular connection that they needed, and you're tossing that out, right? So you're destroying users' work, and that's really a bad thing to do in any user interface. And timeouts are one of the sort of triggers for throwing away users' work. There are other cases where this happens sometimes in interfaces. Like when I showed you the earlier example of you cannot enter a colon in a file name on macOS. It actually not just gives you this cryptic message that says try a different name without telling me what's wrong, but it also throws away the name that I entered. And you might say, well, what's the big deal? Maybe the name was just letter to mom, right? But maybe it was a long, name that I gave it because I had to, copy from some paper a contract number or something into the file name. I had entered that all in, and then it says, oh no, you had a colon in there. Start from scratch, right? You're throwing away the user's work. Don't do this, right? Don't throw away the user's work process. All right, a little bit more on performance. We already talked about the tenth of a second, 1 second, and 10 seconds. Victor, you have your hand up. Is there a question?
Yeah, I have a question. Are timeouts always bad? Because I remind myself when I shut down, for instance, Mac, and there is a 60 seconds timer for automatically shut down. So kind of lockout constraints that gives you some time to think whether I want it to continue. And then if I went somewhere already, so in 60 seconds, my Mac will turn off.
Mm.
I think it's kind of useful and not as bad as it's here.
Yeah. So I do agree. First of all, there are cases in which you end up implementing a timeout, and the timeout. The overall goal that the timeout has in this case isn't maybe not a bad one, right? Saying, okay, I want to give people a sort of safety buffer to act or react on something before I continue with a particular action. But what we have to make sure to understand is that every time we do this, we're basically putting an arbitrary number there. Right? And that arbitrary number, that timeout, is something we pick, and we hope, in our little engineering heads, we imagine there are cases where the time when the user comes back is shorter than the timeout, and those will be all the cases in which the user actually wants to continue. And then we imagine, and all the cases in which the user takes longer than the timeout are the cases in which the user didn't want to continue. And that is completely artificial, right? We know reality is different, right? We know these two are Gaussian curves that overlap, if you want, right? The time that users actually take to complete something is a Gaussian curve, or maybe a Poisson curve, depends on what you look at it. And that we basically put a cut at some point in that curve and say, and everything that takes longer than that was not intentional, right? That was, we were meant to now do the action that we trigger after the timeout. And that just asks for trouble, right? So I think if you do put in a timeout, first thing to do is to think about, is there another way of doing it? Can I avoid the timeout, right? Can I somehow get around it and give people a better interface? If you cannot find a way that avoids a timeout because you don't have anything else that you can offer, then at least think about how can I minimize the impact of the timeout kicking in at the wrong time, because it will, right? And it will almost always be either too long or too short. If there's, for example, one way that you can help with timeouts that appear to be too long is to give users a chance to shorten them, right? The one you talk about, which says your Mac is going to restart in 60 seconds, gives you a button that says restart now. So in that case, I've solved one half of the Gaussian overlap problem, right? I've now said, okay, if you're in more of a hurry than my timeout suggests, you can speed up the process. And that's good. The other direction, it's much harder, right? If you didn't want that timeout to kick in 15 seconds ago, then magically rewind the clock, hard. But what you can do to kind of get close to that is to say, I look at the effects that the trigger has, that the action has, that I do when the timeout happens, and I make sure that the user can undo this action easily with full recovery of, like data he entered, for example, on the Deutsche Bahn website. So the timeout happens, but you make sure that afterwards, if I didn't mean it to happen, I can get back to the state I was in before the timeout as much as possible and easily as possible. Okay, yeah, great question, thank you. So if we now continue on, there's just a quick overview here. And this is something that, those are basic heuristics that people use. For example, developers at Apple get these kinds of directions on how to make sure that your software doesn't suffer in performance, right? And I wanted to share those kinds of things with you, because this is a very sort of real world look at how in industry, if you are really aiming for non-lagging user interfaces, these are the things that people look for. The top performance hit is, of course, the worst thing you can do in a program is synchronous IO operations on external, data storage devices with moving parts, right? That's the worst. This is, of course, less terrible with SSDs these time, but it's still way, way slower than accessing internal memory, for example. And the same is, of course, true for any other kind of synchronous IO, right? Synchronous IO means I do an IO and I'll wait for the result, right? For example, network. But because it's been known for a long, long time that the network is a terribly slow place to be, or can be a terribly slow place to be, there are very good asynchronous APIs that we're used to. We're used to working asynchronously on networking. We're not always that used to working asynchronously on storage devices, because people used to think, oh, that's, there isn't much I can do anyway while that operation is happening, so I'm going to make it a synchronous call. So look for asynchronous APIs in as much as you can to avoid these kinds of things. And in fact, if you can, minimize the number of times where you do access to these kinds of external storage devices in the network, and maybe bundle them in places where the user isn't waiting for things to happen. The second thing is actually a large memory footprint is also a pretty strong performance hit, because while data in main memory is, of course, way faster than on your hard disk, it's actually pretty tricky these days to keep your data in the very fast on-processor caches that modern architectures have. And if once data has left the CPU cache, which is the sort of the level 1 cache, it's often actually faster to recompute things rather than keeping them in memory and trying to fetch them on the right core via a memory access. Examples for this are, in some cases it can be faster to do a computation again rather than creating a table in memory and then looking up the number in that table. Right? Be aware that CPUs are really, really fast, and even accessing main memory tends to slow them down if they need to go beyond their level 1, level 2 caches. And of course, the other effect, which you probably thought about when I mentioned memory, is, oh, too much memory used, and then we get into swapping, right? And swapping then leads to access to the external hard drives or SSDs. And you all know what swapping is, right? I take a bunch of memory from main memory and I put it onto an external storage device so that I can continue working because I think I'm not going to use that. It's kind of like a negative cache strategy. I push stuff out to a slower memory that is much, much bigger. It used to be in the times of, actually spinning disks that you could literally hear your machine starting to swap when it was running out of main memory because the disk would start rattling and continuously moving back and forth, seeking things to put in and out of memory. The third thing is interlocking threads. Explicit multi-threading is really hard to implement. If you've ever tried to build a system that actually explicitly starts and stops and interweaves multiple threads, it's hard to keep this straight, right? It's hard to keep this straight in your head. It's hard to think about all the possible combinations of race conditions, etc. It also often doesn't actually give you much of an improvement because critical areas in for example the OS are often interlocked anyway, right? They're managed usually where you have to ask for a lock to be released before you can access, for example, a particular resource like, I don't know, a sensor reading or an output device, right? So what typically happens in modern languages, like maybe lambdas from C++ or blocks from C and Objective-C, they're actually you capture these small work packages in self-contained closures, and you kind of then just put these into a scheduling system that takes care of them for you, right? It's usually a global dispatching system. For example, like I said, we work a lot on macOS. There it's called Grand Central Dispatch, a little bit of a riff on Grand Central Station in New York. And this kind of central scheduler manages these things and pushes threads out onto different cores, makes sure to balance everything, sometimes even uses the graphical processing unit, the GPU, to put stuff there, and it knows how to best balance stuff out. So that's typically how you do multi-threading today, which is basically you don't think about it yourself. You hand it over, you write the software using one of those dispatching infrastructures in your OS that then takes care of it for you and make sure that it's as efficient as it can be. One performance problem that likes to hit people is iterating over large arrays, where it would be much more useful to, for example, use like a hash map. So basically, iterating over huge arrays means you're running over something that is very long in memory. It probably maybe exceeds the cache that the level 1 cache that you have on your CPU. So constantly you're going in and out. You're caching in the one half of the array, then you're out of cache. You're going to second half of the array. You need to swap out the entire cache content. You do that with every iteration that you do. So that's oftentimes a waste of time. So looking at hashing instead there can help. And a classic that you probably know that's closely related is code that is inside a loop that is invariant, which means it actually doesn't change depending on which which iteration of the loop you're doing it in, that you could actually factor out. So those kinds of things are easy to catch. Or if you have things that where you have, let's say you're running over a 3-dimensional array, you know, so you're doing for every X, I've got a loop, and then inside you have for every Y, I do this other loop, and then in that I have for every Z, I do this other loop. And these can be very expensive. And the idea is there oftentimes you can do these actually quite effectively on a vector unit of the CPU, right? Because vector units on CPUs can process multiple packages of data with the same instruction very effectively. It's called SIMDs, a single instruction, multiple data streams. You probably learned about it in your computing lectures. So look for these kinds of tools available in your OS and IDE of choice, and see if you can't avoid those nested loops that you're doing there. And then finally, most of the large frameworks for Windows and or Mac actually have highly efficient APIs today for a lot of things. And one of the things I keep seeing with students is that they think, oh, I need an object recognition, so I'm going to write an object recognizer, you know, from scratch, with like looking at the data, and then I'm going to filter the picture, and I'm going to do all these steps, and I'm going to write all that code myself because, hey, I took computer graphics or computer vision, so I know how to do that. And that's nice, you know, it's a nice exercise, and for learning how these work, that's great. But if you really are trying to build efficient production code, look for the library, preferably the one that, you know, the hardware vendor or the OS vendor gives you, and use it, because they know exactly how to squeeze the last % of performance out of their implementations. They can work perfectly with the rest of the OS that they have available, with the rest of the hardware even. In the case of especially like vertical design, you remember the golden rule there. So, and these have been highly optimized. They're tested a lot. You'll find a lot of, you know, information on Stack Overflow using those. So in the end, if you reinvent the wheel, then you typically only reinvent one kind of wheel, and that looks like this on the Mac, which is sort of the spinning wheel of death, which indicates that the machine is busy and not responding to input. Okay, so that's a quick overview of some more maybe technical performance tips that I think will help you link the things that we are striving for in the UI, you know, the responsive systems that fulfill this 0.1 second response time for discrete events, with the more sort of, you know, down to earth implementation techniques. Now we're going to stay with a slightly more technical and more computer sciencey topic for the last part of this class, and this is notations. What I'm building on here, if you want to read more about this, there's a great book that I've mentioned before, Human-Computer Interaction, the book by Alan Dix and colleagues. Ollie, is that still the latest edition? Maybe you can do a quick check, and we might need to update this if there's been another one of these. But yes, either way, even in that edition, it's actually a very useful overview of these notations. The point of notations is the following. We've talked a lot in DIS1 about how you build or how you design and conceptualize good user interfaces and how you prototype them, etc. What we haven't talked about yet in detail is how do you get the decisions that you've made about your design across to the implementation phase of your project, which may be the same person, maybe still be you, or it may be another part of a team of people who are coding the things that you have architected and designed. And for that, you need a language, and you need a kind of notation to express your interaction design decisions efficiently. So how do we specify user interfaces? Well, in the early days of computing, user interfaces, as you may remember from our history discussion, you know, the von Neumann architecture didn't look at user interfaces in any particularly different way from, let's say, access to a file system or to a printer. So you know, file I/O and stuff like this was just another variant of you know, user input was just another variant of file I/O, and that's still true with Unix command line tools to this day. So the early way of specifying the UI was just as part of the code. And here's a line from I call this back to basics because this happens to be basic code. And there are a couple of problems with this way of specifying a dialog, because what we're doing here is we are specifying two things, right? We're specifying an algorithm which computes the square of a number. Okay, it's a very simple algorithm, right? It's the n times n is the square of n. But we're also specifying a UI, right? We're specifying what it's outputting and what the user inputs, and it even specifies a certain sequence of these things happening and when the calculation needs to happen. All that is in this code. So you might say, well, that's actually nice, right? That's very compact. We got it all one place. So why bother? Why bother with doing this differently? What do you think are, why is this not good engineering practice? Can you think about a couple problems with this? Not with this particular program, but with this approach of coding the UI as part of your overall software project. Victor, yeah.
The coupling, like the data is linked tightly to the view. So kind of we print after we inputted the data, and okay, what if we want to change the print, we need to also to change this n and so on.
Okay, so we have a few things. First of all, what you're saying, for example, I have some output aspects here and some input aspects, and I'm reading a variable, and of course the variable appears in the input and output, and the algorithm, the computation, so to say, is happening in the same place where the view aspect of the software is happening. Correct. So if you think about model view controller, this is not MVC, right? This is not at all MVC. I mean, this isn't even object oriented, but still we haven't split up the model code, so to say, the business logic of our application from the representation of it, of its user interface. So that's a problem, right? And we have the input output in here mixed in with the algorithm, and we also have the flow through the UI, basically the sequence of things happening, have that mixed in. So that's why we want to get rid of that kind of mishmash, right? When the interface gets more complex and the backend gets more complex, you want to tease these things apart. Can you imagine a couple reasons why it would be nice to have these things specified? Let's maybe start with a very simple thing, a separate file. If we could specify the interface in one basic file, and then we specify the algorithm, if you want, in another basic file. We still stick with the language here, but what would be an advantage already of that? Think about internationalization. Think about, you need to translate that interface to French. Do you want to plow through all the basic code, all the core source code files, that are there? Yeah, Jasper?
If you want to translate it, it gets really hard because, for example, the number is always at the back. And if you want to translate that sentence, that will mostly not work out in any other language than English.
Right. So you actually would have to change that print statement quite significantly. And you would have to sort of, mix things around, move stuff around. And you would also be working with, through all the source code files, right? Aparna?
Yeah, I was just going to say that if you look at websites like Amazon and all, they have done it pretty well now that in Germany it changes to German, and if you're in US, it probably prints in English. And the way they would have done is that instead of putting this as I think I'm getting too much into technical stuff here, but instead of putting this as a static string, what they do is they have a bunch of language files for a particular string, and then based on the region, they output those strings, and that supports internalization very well.
Yeah, absolutely, Aparna. And yeah, that's not too technical at all. That splitting up is the first step, right? Because it gives you the advantage of it's easy to add another language. You just add another translation file. You can actually give that file to a translator and they can work on it. And they're not going to mess up your source code, right? And then if we think about it one step further, that person wouldn't actually have to write C or BASIC or whatever, or Java or JavaScript anymore. They can actually write things in some other language, right? Where they specify the texts and the Maybe there are visuals that also need to change based on language or region. So they can specify that in some other kind of language that is more suitable to that task. Right. And yeah, websites are a perfect example. When you switch the language, you obviously, Amazon isn't coding 15 identical websites with, 15 parallel source trees. They basically have one where they then plug in the different languages. All right, good. So we don't want to mix up UI and algorithm as we do in normal programmings, and that makes it hard to distinguish, things that the system does and things that the user does. So this whole basic split gets hard to see. Another aspect that makes it easier if you can actually pull these things out is if you've ever written some non-trivial input code, checking for errors on user input is actually pretty tough, right? To make sure that people enter, when they enter a date, for example, on a textual command line interface, and to make sure that they really enter a valid date takes a bit of coding. And that has nothing to do with the back-end business logic of your software. It's just to make sure that what the user enters is in the right format. And so that can actually dominate and complicate the code. So you kind of, you can't see the forest for all the trees because you got so much error checking code in there that you don't see the actual structure of your code anymore. So the first step would be to, stay with the language that you have, but at least create different classes or files for your user input and your user output, right? To sort of split things up like that. And I used to work that way when I wrote programs as a student for a lab I was doing a heavy job with. I would at least go in and, this was all written in C++, but at least I was trying to make sure that I have a couple classes that have nothing to do with the UI, and then the other classes were the things that had all the UI stuff in there. The second step then is, as we just mentioned with the example of websites, to use a more efficient or readable language to specify the dialogue itself. Because honestly, all our programming languages are not really good at specifying a dialogue in themselves. And you can do that in two ways. You can actually say, I do this a priori, so I do this before I actually start with the implementation. So I design the dialogue, and then I have a dialogue description, a dialogue definition, a specification of sorts, and I then give that to implementation. Or it can also be used as what you could call an executable specification, where you can actually use the description and plug it into your code, and it actually describes the interface in a way that is machine readable and can be used as part of your actual implementation. That would be the case, for example, when you design a UI with things like interface builder and Xcode, or the visual interface design tools in your favorite IDE. So the problem then is that you need to describe the proposed design of a UI, and you can take a couple different approaches there. We're going to first look at look at this from a language, from a linguistic point of view, computer science languages point of view, and because that means that a lot of the standard computer science techniques can apply to this. We can use the power that we have by, computer science is really good at dealing with formal languages, right? It's something we do really well, and so it helps us to think about the specification as a problem of finding a good formal language to describe the UI. However, the more modern the UI is, the more it is about GUIs and events and things happening all over the place. The harder it becomes to describe it textually. But we'll start with text anyway. For example, if you take a classic Unix command line system, right? This is really easy to describe textually, right? Because there is a clear turn-taking dialogue happening between the user and the system, right? The user enters a string of characters, hits enter, the program parses what got entered, decides what the commands are, the arguments are, executes the command with the arguments, returns some output, and then it's the user's turn again. So this is basically easy to model in a textual, formal language description. The the modern UI where you click here and you open a window there and you switch to a different application and you drag something from that application into your current application, that gets very quickly hard to describe in a purely textual description. But we'll see some examples of how we can do that. And before we do, let's do a little bit of a mini brainstorming here. You guys have all taken theoretical computer science classes. So let's hear a couple suggestions for formal notations that you've met, that you've come across before in your studies that maybe we could use to specify a UI as well. So what kind of formal notations have you already seen in your programs, in your study program? You've all seen some, I know. Formal notation, is a very broad term, right? Anything that helps you to formally specify a system. Yeah, Victor?
HTML nested text, we can build blocks with divs and in block structure specify our UI.
Okay, so we can use this sort of nested, like the document sort of object tree kind of thing that we do with HTML and nested commands there, yeah. Or more generally, like markup languages. Yeah, that's right. What about other things? It doesn't necessarily have to be all textual. Come on, you've all taken classes in formal systems and stuff like this. Yeah, Julia.
Yeah, so oh, wait a second. We'll go.
No, we can hear you, okay?
Yeah, my microphone was up. Yeah, I can't remember the name. I just tried to look it up, but I can't remember the name. It was like you could choose like different parts of the sentences to structure the requirements that you want to show or that you want to be implemented. And yeah, it had like different default possibilities to choose from to create those sentences, and in the end you have a whole requirement over.
Yeah.
I can't remember the name. I don't know.
What you're describing sounds a bit like grammars. Is that what you mean? Where you derive? Okay. Well, keep looking. I want to see which one you are referring to. I don't know at the moment. But grammars were actually one of the things that I have in mind here, because grammars let you specify, certain sequences of events or constructs or language constructs, which then means that if you could parse a sequence, you can execute a certain. If you can parse a sentence, you can execute a certain sequence. Jesper.
Yeah, I thought about something close to grammars, an input-output automaton.
Yeah, look at that. Automata, right? In general, finite state machines or finite state automata, they are super powerful. We use them all over the place in computer science, and we will actually be using them here as well. Victor, you got another one?
Yeah, as you told that we can use non-only textual interface builder in Xcode, where we can basically place some elements on the screen and then connect them with the code.
Yeah, so doing that actually, I would say, I would less call that a formal notation from theoretical computer science. It's more like using an actual tool, but you're absolutely right. You are specifying the UI, and you are specifying it with a computer with computer support. So in a way, it's a formal specification, just not in the same way as a theoretical computer scientist would probably scoff at you calling interface builder something to create a formal notation. But for sure, it has, of course, the advantage that it's immediately executable, right? It becomes part of your project. Okay, so we've mentioned state machines. We've mentioned grammars, and you may remember things like EBNF, Backus-Naur forms, those kinds of things. And of course, everybody's favorite, the Petri nets. Those are all systems to specify dialogues. Let's look at these. Here's an example in the Backus-Naur form of a grammar, right? So for example, what does this describe? Can anybody take a quick stab at this? What kind of things does this grammar generate? Grammars generate strings, right? They generate sequences of tokens, if you want. And by generating them, they also specify which ones are legal inside in the grammar. So this could be used to specify a certain way of expressing certain legal sequences of tokens. All right, you theoretical computer scientists, to the front now, and tell me what this grammar describes. Gotta go back.
Yeah, it's actually a concatenation of expressions. So either one or nothing, or expressions in braces.
Mm-hmm. And if I were to unpack this completely until it finishes unpacking, so to say, what could be a possible result?
As it's recursive, it could be infinitely large string with an expression that we can have there.
Yeah, but in the end, expressions will all go back. I mean, we know that expressions we can continue to replace with more expressions, but at some point we end up with not, no more expressions, right? We need to make this stop sort of recursing. So what is at the bottom? What is the potential outcome of this?
Atomic expression here stated, yeah.
Yeah, exactly. So in the end, I could say expression is just the word empty, and empty is just a token. I haven't told you what that is, right? It could just mean something that I don't know what it is. Well, it could also evaluate into atom and another expression. So atom and empty, for example, or it could evaluate into parenthesis opens, atom, parenthesis closes, and then another atom, for example, right? So this is basically describing a certain way of parenthesized, possibly, recursively nested statements that consist out of atoms, right? Or the empty statement. Okay, so that's one way to describe things. Here's an extension of this that Ben Schneiderman created, one of the pioneers of graphical user interfaces. He termed he coined the word direct manipulation for user interfaces, and also wrote a great book on HCI. That's a textbook in many editions. And he proposed as multi-party grammar. This is an interesting one. And again, I want you to tell me what does this do?
It will eventually end up in log in some name for the user, for example, then hello, and some other name for the responder, for example. Okay,
so yes, and the cool thing here is, if you think about it, so it will definitely put out the word login. So this means that the user will start, right, entering login and entering a name that the user provides, and then the computer will respond, because that's the responding part, with hello, and then repeat the username, right, the name that the user entered. So what this describes, we don't need to talk about the details here, but you can see this can describe that's why it's called a multi-party grammar, a dialogue between computer and user, right? So in certain parts of this grammar are things that the user will trigger, and other parts are things that the computer will trigger or fill in. So that would be a way to describe, command line GUIs. Like, this was obviously the logon sequence of a system that where you enter logon Bob, and then it says hello Bob, right? So this works great for command line user interfaces like that. It works great for things that have very simple dialogue progress, like banking automatas, like banking machines. The ones where I love that expression. Did you know that the Dutch have a name for banking machines that is pulling money out of the wall? I love that. So that's banking machines in Dutch for you. Or Unix commands, for example, if you look at the man page from Unix, it actually will give you an expression at the top, right? A regular expression, a regex, that describes all the ways that attribute or arguments to a certain command can be triggered. If you haven't seen those, definitely take a look at a man page from any kind of Unix command, and you'll see that. I think we may actually have an example coming up, I'm not sure. For GUIs, this isn't so great. For GUIs, this isn't working as well because there is no as obvious sequence of steps in a GUI, because people can do a lot of things at any time, and that creates something that is actually better captured with something else than these regular expression kind of things. Yeah, here's the example I was talking about. Sorry. this is a very simple regular expression that I'm sure you've seen. You know what the asterisk means in a regex. Again, take a stab. What could this describe?
Yeah, maybe selecting a line, clicking at least once, then clicking a number from 0 to infinity times, and then double click.
That is very close. Not quite, though. Julia, do you have an idea?
I would have said the same.
Okay, so you're very close. Victor, you can take a step.
Yeah, it's kind of selecting several lines and then do something with the context menu with all of them.
Okay, you're all very close. What's a little bit maybe misleading here is that select line itself actually stands for you picking the command to draw a line. So this is selecting the line drawing tool. Right? So we click on the line drawing tool, and then you click once on the canvas, and then maybe 0 or more times. And then when you double click, I guess, Eugenia, that was what you were gonna say. Yeah, when you double click, thank you, you then complete the line drawing. Right, so that's what this is describing. So we kind of understand click immediately. Select line was a little bit, you don't know what it means. And that's the point, right? Regular expressions describe syntax, they don't describe the semantics, right? You don't know what's behind it, of course. Here's another example taken right from the man page for the well-known Unix copy command. So if you've used that on the command line, that is a regular expression, right? It tells you that the Unix copy command has to have the letter CP at the beginning, and then you have all these options. Some of these are alternatives with the vertical bar, and the angular brackets mean that they are optional in general. They don't need to be there. But what needs to be there for sure is a name for the source file and a name for the target file, or a name for the source file, more names for the source file, and then one target directory. So man pages use this, right? This specifies the recursion policies, how copy commands should be recursing into directories. And the second part of optional things here, of which you can pick one, -f, -i, or -n, specify the overwrite policies, whether it should delete duplicates without asking, or whether it should ask you, or whether it should ignore them and skip over them. And those are the same things you get asked by your system today. If you're like on a Mac, you copy a bunch of files into a different directory, it will ask you the same things. Should I, replace them? Should I apply that to all of them or not? But here with the command line, of course, you express that in a textual form. Okay, these are short. They are precise. We know we can turn them into code, right? They are actually very well formalized, but they are not easy to read, and they do require extra information about the semantics. As we noticed, it was kind of hard to say exactly what this first regex actually did, because if you don't have the background knowledge of what people were trying to express with this, it's not in the description, right? It's just the syntax, not the semantics. Now, we're going to look at another example here called production rules. And again, you will probably remember these from your theoretical computer science lectures. Production rules are just a bunch of rules that is not ordered, that basically give a certain condition, each of them, and then says, if that condition is true, then the following action can happen, or will happen. And these conditions will change based on the system's state and or on events that come in. Both the blessing and the curse of production rules is that every rule is always potentially active, right? Every rule could fire if you want at any time. This is great to model concurrent behavior, but modeling sequence with it is very awkward. So if, for example, you have something like a graphical user interface where there is no one clear action sequence that will happen, then you tend to be covered better with a production rule system. And I'll show you an example of an event-based system for production rules. First of all, remember the select line thing that I mentioned earlier, right? So where I said we want to model the sequence, for an implementer that says the user should first pick the select line tool. They should be able to do that. And when they do that, there will be one or more clicks, and then finishing with a double click, and then you should, draw the line. and go, and then that sequence should be done, so we should be back at the regular sort of default waiting state of the UI. Now, doing this with production rules, because this is a fairly clear sequence, is a little bit cumbersome. You will have to work with tokens in production rules to make that work. So, for example, I could provide the first production rule, which says, if I have the select line token available, the production rule can fire and create a token called first, which in other words means I now have basically a helper token first that I need in order to generate a certain sense of sequence in this production rule collection here. I have a second rule that says, if I get a click event and I have a first token available, then I can then generate a rest token. And if I get a click and I have a rest token, I can also generate a rest token. If I get a double click and I have a rest token available, I will draw a line. Okay, so what we did here was basically we imagined a system where we have an event queue of events coming in. More about that in DIS2, how you implement these, how they get handled, how events make it from a user's mouse, input device all the way into an application. But you imagine the list of events coming in, and first and rest are really just helper states here, internally generated events, you could call them also, or tokens that help you to step through this. So why does this model the same thing that we saw earlier? Well, because for these rules to fire, for all of the rules number 2, 3, and 4, we need a first or rest token. That means these are not available until the first rule has fired, right? So the first rule will be the first one that can potentially fire ever. And for that to happen, the select line thing needs to happen, which is the event that the user picks the line drawer tool, right? So this is where the user picks the line drawing tool. Once that has happened, we've internally generated this first event, if you want, and put that onto our queue. And then if the user clicks and that first event is available, we can generate a rest event. Once the user keeps clicking, and again, these other two production rules cannot fire because they need this rest event available. Now we have a rest event available, so these other two rules are the only ones that can go off. So we have click and rest, which means we'll generate more rest state events, and then we have double click, and that then actually leads to the draw line action being executed, because it signifies to the system that the user has completed their input for the draw line tool, and the line should actually be drawn with the points that the user has specified on the map. Now, of course, what's interesting here is that while the user is busy drawing here, they could actually pick the select line tool again. And that would bring us back into the first state here, right? So, and we have to think about, that's where it gets interesting. What should happen if the user starts drawing a line and then clicks on the line selection tool again? Here, you as a UI designer is responsible for specifying following the principle of least surprise and all these other good things on what should happen when users do that. If you don't specify it, your specification is incomplete, and the implementer will build something that they find usually technically easiest to build, or they will just ignore that case, and some default behavior will happen that may or may not be what you want to see from a user experience perspective. Okay, so this is not good at modeling state. As you can see here, we had to introduce these first and rest helper events to model essentially what you could call state, right? And I know you're all eagerly, like scratching with your hooves, because automata, finite state machines or state transition networks. It's all the same thing. Endliche Automaten, that kind of stuff. And that's exactly what works so much better here. So let's take a look at these next. State transition networks are one of the most common tools to specify the simpler kind of dialogue. It's a super established format. They've been around forever, and they consist of states and transitions, right? They are the famous bubbles and arcs, things that you've been drawing in, the formale Sprachen, Automaten those kinds of lectures. So any lecture that taught you finite state machines or automata has covered this ad infinitum. one thing that's interesting here is how does that map to user interfaces, right? You know, states and transitions are what makes up a finite state machine, but what do the states and transitions represent? And that is interesting because the states are usually, well, they are stationary. This is where nothing exciting happens. While an interactive system is in a state, it's waiting for typically some kind of user action or maybe an external action like, you know, I don't know, an email arriving or something like that. And it's not doing anything. So nothing's happening inside the state. It's waiting for stuff to happen. What happens are events coming in from the user or, you know, externally, like I said, like an email arriving, or, you know, the printer reporting out of paper or print job finished. And then the transition is the arc from one circle to the next, and that has this action on it, and it has the system response, what the system does as a response to that on it. So all the things that are interesting are actually happening in the transitions. The states are just there to rest and wait for more typically user input if you're modeling a UI to move on. Okay, so this is really, really great for modeling user action system responses in a fairly flexible way. I will show you an example. I should explain maybe one more thing. I'm saying nothing happens inside a state. That's not technically true. Because, for example, inside a state where the system is waiting for some user input, it is probably still running, for example, screen refreshes, or it's doing things like scanning the mouse, you know, event queue and stuff like this. So on a lower level, there's always stuff happening, but you have to decide, and that's your call as an interaction designer, what is the level of abstraction I am modeling in my diagram? Am I modeling currently, am I modeling the driver behavior of a new input device? Then you're going to be down at very, very detailed things, right? So you're going to have lots of states about like a single bit flipping in your driver. But at a larger level of abstraction, where you're describing, for example, what should happen in an interactive exhibit while the system is waiting for a user to step up to the exhibit and press a button to use it, it might play, you know, a loop of a video while it's waiting for that. And that whole video playing is happening, but on your level of abstraction, it's not an interesting part of the interaction. So your system isn't doing anything, nothing interesting is happening from your point of view at your level of abstraction. This is a difficult level to pick right, and you need to think about this when you write down your state transition network. What am I ignoring, basically? What kind of level of detail am I ignoring, and what level do I want to model and bring out the interesting design decisions that I want to communicate to the team? Okay, so here's an example. And again, I want you guys to explain to me what we're seeing here. This is obviously a state transition network. We've modeled this in the way that you should know it, with the start state marked with a little triangle, and the finish state marked with a double, or the finished states marked with double circles. And in between, we've got intermediate states and transitions. So can somebody explain to me one of the two branches that we're seeing here? What are they describing? Or what's this thing as a whole describing? Yeah, Tejaswini, take a go.
Yeah, so for the first branch where they take the circle one, so you select a circle and then I guess you have this different kind of pointer which will allow you to move it around a little bit. I'm not so sure about that.
Yeah.
And
yeah, not quite, but continue, finish your sentence, sorry.
Yeah, so and then you get another circle, and then like you insert another circle is what is happening, is my guess.
Yeah, okay, that's a decent guess, not quite. You're getting a little bit confused by the same things that happened when we looked at this line example earlier. Remember, these are states of the UI. They are not objects in that the user is creating, for example. Okay, Marius.
I think the circle mechanism works in a way that after you select circle, you click on the center of where you want your circle to be, and then you move your mouse to where you want the circumference to be, and then it draws the circle. And the same goes for the line with the points, basically.
Right. Julia, were you on the same line?
Yeah, basically what you could do for the second line is that you can click on different, so if you draw the line, you can click on several points. So you create like the line with different points in between, and in the end you finish with a double click. But
exactly. Yeah, you're both right. That's what's going on. So this is modeling a very, very simple drawing program, right? It's a drawing program that only has a menu to either draw a circle or draw a line. And when I say select circle here, I mean the user selects the word circle in the UI from a button or a menu bar. And that moves me into a circle 1 state in which he can then, for example, click in the center, and that will generate this rubber band drawing of a circle with dotted lines. So I can start drawing this. And in circle 2, I'm in that state where the user is moving the mouse around. The rubber circle is following. That's not specified here. So rubber circle is a sort of a rough description that would have to be detailed out for a proper interface description. But then once the user clicks again, it means that he now clicked where he wanted that circle to be with its circumference, and then the circle gets drawn. So beneath the arrow, you can always see the system output, and above the arrow, you can always see the actions that the user took in this case, right? Good. And yeah, as Julia said, this is the same case with the line, except we have an option to draw what's usually known as a like a multi-point line or something like that, a multi-segment line. Good. So I want to give you an example of how to model systems behavior with that approach. And the first one is going to be from an exhibit that I built, 20 years ago. That's why I look surprisingly spry and young in this video. So this is a conducting exhibit that we did. Yeah, everybody's like moving up to the camera now to see this. That's funny. So this is an exhibit that lets you conduct the Vienna Philharmonic on a big screen, and you will basically, you can listen to the video here, and we'll go over the actual sequence of events that happen here. So pay a little bit of attention to the different states that the UI goes through as we do this.
The House of Music Vienna is a museum documenting the city's rich musical past, present and future. It is located in the heart of Vienna, Austria's capital. Its third floor contains 2 exhibits designed by our research group. One of them is Personal Orchestra. This system lets you conduct the famous Vienna Philharmonic. Entering this room, you find yourself in an environment reminiscent of a classical concert hall. On a large video projection, you can see and hear the orchestra rehearsing. Reading the 1-sentence instruction on the screen, you walk up to the conductor's podium, pick up the baton, and press the button on it. This baton is all you need to use this exhibit. Moving it up and down and pressing the button lets you select your language. The next screen explains how to conduct and lets you select a piece. We will choose the Anna polka. Now the orchestra waits until you start to conduct. The size of your conducting gestures determines the volume of the orchestra. Conducting towards individual instrument sections raises them above the rest of the orchestra. But best of all, the orchestra follows the tempo of your conducting, using a special algorithm to change audio and video speed in real time without changing the audio pitch. However, if you conduct too fast or erratically, the orchestra will stop playing and complain.
Ihre Schlagtechnik ist ja völlig unprofessionell. Das geht überhaupt nicht. Das erinnert mich an das ganz alte Sache am Dirigenten, die überhaupt nicht dirigieren konnten.
But if you conduct well enough, you will be rewarded with a big applause and your players raise themselves. After that, you can pick up a certificate at the museum shop to show that you conducted the famous Vienna Philharmonic Orchestra. This way, Personal Orchestra lets anybody experience what it is like to conduct the Vienna Philharmonic, and that conducting is much more difficult than it seems.
Okay, so that's our exhibit. It's been up there since 2000. We've overhauled it a couple times. I think 3 million people or more have now used this in this museum. It's still running there. In fact, we're just doing a new revision now after 20 years of the system. And I'll be honest, we used the frantic applause from a Michael Jackson rock concert in that sequence where the orchestra had finished playing. A great project, was a lot of fun recording the Vienna Philharmonic, sitting in the house of, in the Golden Hall where they do their New Year's Eve concerts that you guys know from TV, and telling them what to do. That was fun. But what I'm trying to point out today is how did we model the interaction with this, and how did we talk to the museum and the orchestra about the exhibit and how it would work? How did we agree on an overall sequence here? So I'm going to show you an STN that we made as part of this. Don't worry if you can't read this. I'm going to zoom in on that in just a second. You see here basically all the states that the system had in general, and I'm going to zoom in on the start here. So when the program starts, that's sort of the external event happening, and the reaction of the system is to show a video loop that is the orchestra rehearsing, right, while nobody is using the exhibit. And then, so that's basically happening in the intro loop. Now, if the user actually clicks, somebody walks up to it, a visitor, and clicks on that button on the baton, we wait for the video loop to end. We don't, immediately jump out of it. And then, the intro loop, once it has ended, we then switch to a language selection screen, right? So then we are in this state where the user can pick a particular language. And as you can see here in this language selection screen, there's stuff happening, right? We're highlighting one or the other language, but that's not modeled on this level of detail here. And then the action that happens is basically that the user clicks a button to confirm their language selection. And at that point, we then switch to the next screen, which is the piece selection. And then here, we actually have a state in here that we later discovered wasn't technically necessary. So we basically directly move to continuously display the current piece selection. And here the user picks the musical piece. And then when he clicks again and has picked a piece, we then move to the next state, which basically says we've now chosen the piece. So then the other thing that could happen here is if somebody wanted to get more information about the exhibit, they could do that. But if they don't, then we start basically with the orchestra waiting. And if you then start conducting, you start moving your arm up and down. That basically suggests that we are now in the state of actually conducting. And the interesting thing is, FSM conducting, this finite state machine here, state is the whole thing happening while the user is conducting. So while the user is normally conducting, a lot of stuff is happening. We're playing back video, we're time stretching it, we're moving, we're panning left and right. All that is not modeled in this overview for a reason, right? We didn't want to go into detail in this overview. So there can only be two things that lead out of the state. Either you made a mistake by conducting too fast or too slow, in which case we go to the complaint sequence, which then will take us back up to the piece selection screen, or we have completed the piece successfully, in which case we get this, rousing applause and then go back basically to the system's start screen. What we do by this modeling is that we can actually see certain design decisions. For example, the fact that what should happen if somebody gets a complaint, right? You could say, well, if he gets a complaint, we could just go back to replaying the piece so that the person gets a chance to play the piece again. But we don't. We give people a chance to change the music because maybe they want to pick a different song after they failed conducting one. And so those are the kinds of design decisions that go into this, that are expressed in this notation. A little bit of a more modern example, in 2000, I got to think here, I think 2010, we were selected to design an exhibit for the German pavilion at, an extension of the German pavilion, I should say, at the World Expo, the Weltausstellung, that was happening in Shanghai that year. It's this big thing happening every, I think, 4 years or so, where every country gets a pavilion, and somehow Germany got a deal to get 2 pavilions, so we were able to design something for that extra pavilion. In fact, designed the whole experience in that extra pavilion. What we made was a little bit of an immersive experience to create a neighborhood, create the houses and the plants and the infrastructure that's needed for a city block, because the whole topic of the expo was that the city of the future, and we wanted to kind of point out the fact that you need to take care of your immediate neighborhood first to build a great city to live in. We knew that all these other exhibits at the time were being designed, all the other pavilions were designed as, touchscreens had just gotten really, really, everywhere. So everybody was designing touchscreen experience. So you had to like touch, and read, and it was very boring. I got some kind of like touchscreen allergy, I think, that year. So we wanted something else. We wanted a different kind of interaction. So we gave people something where they could actually walk in and stand in front of this big screen. And what we were tracking were their full body gestures, like what were people doing with their whole body, and that was controlling the exhibits. I'm going to again play the video so you get an idea how this works. This is a bit noisy. This is where we are training our helpers who were then guiding tourists to this exhibit for the next 6 months or so. We're training them to use it, so it's a little bit chaotic, but you kind of get the idea with these little pictures that we're showing here.
Hier heute die Möglichkeit, selbst unsere eigene Stadt zu bauen. Wir werden unsere Stadt gemeinsam in der Gruppe gewechselt, wo uns jetzt eine kleine Stadt findet. Und es funktioniert in 4 Schritten. Zunächst macht ihr Häuser, dann Strom, dann erzeugt ihr Bäume und dann erzeugt ihr Wasser für die Bäume.
是自己建造自己的城市，有房子、电、树木和水。
Um die ganze Sache zu erzeugen, benutzt man seinen eigenen Schatten, so wie beim chinesischen Schattenspiel, ganz traditionell. Das heißt, ihr gleich anfangen zu spielen, bewegt ihr euch ins Meer und erzeugt das nächste Dokument aus.
是用自己的影子盖一下房子，看到了吗？
Machen wir große Häuser, kleine Häuser, ganz breiten, wie auch immer ihr wollt. Neues Ziel weiter, ihr geht mal alles weiter. Das soll ja auch nachher.
就是你们的房子到时候有听那个主讲讲话哈，所以安静一点。
Ein Haus braucht auch die Beleuchtung, deswegen nutzt ihr jetzt die Verbindung vom Licht.
现在是用电连起来。
Je länger ihr das verbindet, desto mehr Lichter gehen an eurem Haus.
时间连起来越长，灯亮越多。
Sehr schön. Viele gerne will ich das sehr schön. Gut, das nächste. Als nächstes sind die Bäume dran. Wir wollen ja auch irgendwas ein bisschen Grün in der Stadt haben. Wie bei den Häusern wieder. Ihr könnt verschiedene Arten von Bäumen machen, auch Tannen oder Laubbäume. Ihr könnt auch ganz kleine Bäume machen, aber nicht große. Sehr schön. Vielleicht wird wieder eingefroren. Perfekt. Das letzte, was noch fehlt, ist Wasser für die Bäume. Damit
das ist Schwä.
Und nach rechts.
往上，往上，往上。
下面，下面， das raus. Ich schiebe das raus. Wir gucken uns mal alle 16 Häuser nebeneinander an. Das ist eine Fassade. Und diesen Stadtquadranten, dieses Viertel, könnt ihr unter der Nummer da unten, 3537, im Internet nachgucken. Gleich beim Rausgehen bekommt ihr einen Kühlschrank-Pin, auf dem die Nummer auch nochmal eingetragen ist. Genau, und dann gehen sie alle raus. Das war's.
Okay, lots of fun, as you can see. People were having fun creating this thing. Just real quick, again, we used an SDN-like representation here to show what's going on. First of all, this is the setup. So we got 16 screens here with lots of video, large video projections, several computers, one running as a server, and these others were running as clients of that server. Then there was, of course, a web server hosted that had this microsite running, and that was sending pictures because we were taking photos actually of people as part at the entrance, and that was also part of the online experience that you could then do after following up. The key point here is, I'm not going to go through this in detail, but again, we use this representation of states and transitions to show how this works. This is not a conventional notation, it's a kind of an unconventional notation, but the important thing is that we agreed in the team on how we would present everything. Like we have a state here, and if a timer expires, in this case, we have a lot of timers because this was a timed experience, kind of like a Disney ride, then certain things would happen. But if somebody, for example, pressed pause, this could be done by the controller who was running the exhibit, then the timer would be stopped and would, you would be, for example, in the pause state in this case. So lots of states for, initializing the system, asking people to step up to it, giving a welcome screen, building a pose, counting down, and then taking, a first flash to get the building, and then same things for the electricity, water, and the final one that kicks people out and then going back up. That's sort of the server state, and the clients were just really simple. They were just essentially sitting there waiting for messages from the server, and then continuously doing the things that the server was telling them to do. So they were driven by that. So we only had one state machine essentially, and all the other machines and all the other computers were hanging off that single state machine. And what we were able to do with this was that we actually could then, in a later design, we could use this state transition network notation and actually use the same design in our storyboard, right? So here you see four columns. The left side shows you what the visuals are that this particular state shows on screen. So it's very easy to understand for somebody who looks at this. The next one gives a textual description of what happens in that state. The next one is our technical description of the server-side state and action. And the fourth column shows the client-side state and action of each of these things. Again, feel free to go through these at home if you want to take a closer look and think through how this layout works. I'm just going to show you these things from posing for a building and countdown to through posing for the electricity connections and posing for the trees. And then finally for the water, then you had everything together, and then we basically kicked people out of the exhibit and got the next group of folks in. This was like a 3-minute experience, I think, overall. So we piped hundreds of thousands of people through this exhibit in the few months that it was running. Okay, so this is great, right? This works great for SDNs, and there's a way to improve on SDNs by boxing things up, right? SDNs can get messy if they get big. So one trick is to use basically hierarchical SDNs. Here we have the start and finish states of a sub-SDN serving as kind of like the connection points, the glue points, where I can connect them into a larger structure, right? So for example, here, you may remember the menu that we saw earlier with the, drawing lines and circles. This could be the graphics submenu here that I get into when I select the graphics menu item at the top. Then maybe the menu bar drops down and says, line and circle, and then I'm in this submenu. And once I'm done in that, I go back to the main menu state, right? The expressive power, theoretically speaking, is the same, but it makes it more convenient and easier to see and get an overview of something. So you could specify an entire system this way. So it gives you a chance to get a sort of hierarchical overview of your SDNs and get complexity under control in that way. So how would we typically use this? Like you saw in the example, especially I think for the China exhibit, for the Shanghai exhibit, create a simple SDN for the dialogues that you envision, then create a UI snapshot. You can sketch it if you're still in the paper prototyping state, label it with a name, include some off-screen area where you put annotations or extra buttons that simulate user actions. Again, similar to what we did earlier on in the prototyping lecture when we talked about this little shopping cart example where you had like a scanner and stuff outside the main screen. Anything that you cannot simulate with a simple click on the current screen should be in this off-screen area. And then you can walk the user or the client or whoever you're talking to through your paper prototype, consult the SDN as kind of your backup to tell you how to respond to each user action. And basically the SDN is the smarts, is the intelligence behind your paper prototype, right? It's the structure behind it. It's very much like a flip book with an additional kind of knowledge of how things work. An alternative, of course, is that you can let the computer execute the SDN itself because, hey, it's an SDN. Computers are made to execute these things, right, to run them. And for that, you can use things like Keynote or PowerPoint to do that. And you get then in basically the same benefits that we've seen earlier in the prototyping lecture. Here's again the example of the main menu and this graphics menu. So what we're showing here is basically we're going to next show you a simulated interface in Keynote that uses this SDN model behind the scenes to run the user through a sequence. Okay, so it's the one that we've seen many times now. And here's the example. This was originally implemented in HyperCard, which is a system that has been long gone, but it's a bit like Keynote or PowerPoint in a way. You can imagine it. So thanks to Ollie for porting this over to a modern implementation of Keynote here. So imagine you're prototyping graphics to a drawing program, and so far you've got the main menu state here, and you've got the graphics menu, and you haven't implemented yet or thought about yet what the text and paint menus are going to look like. So far you've only thought about the graphics menu, so that's the only one we've implemented. So I can click on the graphics menu bar. This is a very simple menu bar here, right? And it looks like I've already drawn some things. I click on the graphics menu bar, and down drops a circle and a line menu, right? Okay, so I can pick any of these two. These will look very familiar because, like I said, we're running the same SDN that we talked about before. I'm going to pick the circle tool here. And so what now happens is I can now, I cannot even pick a random place here because this isn't a drawing program, right? I'm simulating a drawing program in this prototype here. So I'm suggesting that the user will click at this location here. And I simulate that click on this location by pressing that button in this. And that's why I have this button outside the UI of my prototype here. So let's assume the user clicked there. What would then happen is that a circle appears, and then I'm already directly moving to the state where the user then has found the right size for the circle. I'm not showing the animation in this version here. And I assume that the user would next click here. And if you did that, which I simulate again as a designer by clicking on that external button here, I've now created a circle, right? That's how drawing a circle in this program would feel. But I'm now at the end of this sub state, right? And I need to move basically back to the main menu state. Now, if I click this button here, this will take me back in my SDN to my starting state. What's going to happen to the UI, you think? What's the UI going to look like when I press this button? Jasper?
I guess the newly drawn circle will be gone.
It's gone, exactly. And that's super important to understand because we're not simulating a tool where you can draw a circle after circle. This is a very limited simulation of drawing one circle. So if I press this, I'm back at the starting state, okay? And you can see the different states here. This is a helper menu that I have as a developer to pick directly certain states that I might want to go to. As you can see here, it really only has these few things implemented. Not even the line thing is implemented here as detailed drawings, okay? But you can see if I were to go out of Keynote presentation mode here, you can see this is just a bunch of Keynote slides that Ollie made sure we jump back and forth in the right way with links between them, similarly to what we've already seen in the simulation of the website prototype for the computer science department. Okay, so SDNs are great because we know what to do with SDNs as computer scientists, right? We can check, for example, completeness. Can I get anywhere from anywhere? Are all the possible actions covered in every state? Or how easily do I get from one state to the next? You can actually run a quantitative analysis on that aspect because computer science has all these amazing tools for working with SDNs for reasoning about automata, right? We know whether automata have unreachable states. We know how to check that computationally. So all of this can pay off and be used when you model your interface as a state machine. We can also check things like reversibility. What do I mean by reversibility? Well, if I, for example, clicked on the circle tool and I made a mistake, I didn't want the circle tool, how do I get back? And that's something that the state machine would have to reflect, right? There would have to be some kind of action that goes off from there that takes me back to a previous state. Remember that just reversing to a previous state doesn't necessarily mean that it is an undo, right? For example, if I have a button that says print, and I hit the print button, I'm in the state that says printing document, and then I have a button to go back to the previous state, it doesn't unprint the document, right? That's impossible. So not all things can be undone, but we can think about reversibility by just looking at the state machine, not thinking about the semantics behind it, just analyzing the heck out of it with all the tools that computer science is available for working with automata. We can also look at dangerous states because there may be some states you don't want to get to, or that you don't want to get to by accident or too easily. And those are things that you can also check easily with a state machine. Let me show you some examples. For example, here we've got our graphics menu again. And if there is any arc missing in this graph, that means I haven't specified what should happen if the user does that thing or that event happens in this state. For example, let's say the user, opens the menu, picks the circle menu, and he's here now. And what happens if he immediately double clicks here in circle 1 or circle 2? Double clicking is not defined here, right? We're not saying how to get out of these states if a double click happens. So by default, that means nothing happens, right? The input would get ignored. If somebody just took this implementation or the specification and turned it one-to-one in an implementation, the only way to get out of circle 1 would be by clicking on this, clicking somewhere, single clicking, and specifying that that's the start of the circle. So any arcs missing, specify, or mean that you haven't specified what should happen. And this is often helpful to think, wait, users could do that. What should happen? What's the logical thing to happen? What's a good way to react? Principle of least surprise, right? All these good things. Another thing is, when you have the double click, I'm sorry, this is just explaining that we have double click in the line here, but we don't have it in here in circle 2, for example. We also have other issues here. This was the reversibility that I talked about. So let's assume, I've basically started here and I've clicked on the line tool, and now I'm here. If I click on the first point, I end up with the rubber hand here and go to line 2. And then if I double click again, I'm in the finished state, right? And this is basically similar to what you imagine when you go through basically because we enter the graphics tool here, the graphics submenu. So what this is showing in the current implementation, it means even if I entered the line drawing tool by accident, I have to draw a line to get out of it. The current system does not allow me to undo my selection of the line tool until I've drawn a line. Obviously, that's bad design, right? So this would have to get fixed. And what I'm showing you here is that these state machines give you automated ways, because state machines we can process with computers, to find these holes in your specification and point out that you need to think about them. The design is still your challenge, but it can help you find these points. Another challenge is dangerous states, as I mentioned, right? Let me give you an example. There was a word processor back in the old days that had two different modes. There was an edit mode and there was a main menu mode. This is similar to how VI works, right? We talked about VI. The F1 key used to be used in that editor to change the mode. So it toggles between the edit and the menu mode, okay? Every time you want to toggle, you hit the F1 key. The F2 key lets you exit the program and save the code and save your current file. It's a text editor, right? And this can only be done when you're in the menu state, obviously, as you can see here. And escape doesn't change the mode at all. It stays basically in the main menu here. But escape is used to reset the autosave. What do I mean by this? Well, sometimes you may you may accidentally modify a file, and the system automatically saves things, and it knows, oh, this file has been saved, so it will ask you to save the changes. Whereas if you accidentally change the file, and you're like, oh no, I don't want to save these changes ever. I just accidentally, fell on my keyboard. I don't want to save. You click the escape key, and it would suggest to the system, this file is like it has never been touched. I can throw this away without saving because the user considers this not to be something I need to save in this new version. It can stay as it is on file. I'm ready to discard any changes. Okay, so it basically takes away the autosave. Well, autosave is maybe the wrong word. It takes away the changed flag of the file. Okay, so far that's fine, right? Of course, you never want to exit without save unless you really intended to, right? So I can be in the edit state here, hit F1, be in the menu state, then hit F2, and it will save and exit. That's good, right? That will be like the 99% of all cases standard procedure. If I make if I'm editing things and I have actually changed anything, I can go back with the escape key. By hitting the escape key, I will get into this what I call the red states. These are the states in which the save changes flag is cleared, right? So the system thinks you don't want to save your changes. Of course, if I'm in that state, I've hit the escape key, or I've loaded a fresh file, and I do any editing by going to F1 and doing any update, then I'm back in the save blue area, right? Where any changes that I do will get saved upon exit. But let's assume I edit a bit, I'm in the blue state, I hit the menu key, I hit escape, and then I hit F2. Then I would exit without saving my changes, right? Now, so that's something that you may want, but it shouldn't happen accidentally. And sure enough, the original keyboard for which this was designed, the keyboard that the developer of this software had in front of them, was an old style, like, Sun computer keyboard that looked like this. The function keys were on the left-hand side, kind of like with the Xerox star, the dedicated function keys. So there was a whole generation of keyboards that had the function keys here blocked on the left-hand side. In this case, no big deal. The escape key is way up here on the main keyboard. And if I hit that, I'm never going to hit accidentally escape and F2 after each other, right? They're far away from each other. There's a gap in between. But guess what? If you get the new keyboard layout that you guys all know, where the escape key is right next to the F1, F2 keys, you could actually intend to press F1, F2, which is your sequence for saving. But maybe as you hit F1, your finger also catches the escape key, which clears the saving flag, and then you hit F2, and that's a disaster because without any further questioning, it throws away your changes. So you see, the layout of the keyboard here actually matters, but you can actually analyze this whole situation by drawing a carefully thought through state transition diagram. That's the whole point here. There are more properties you can check in state transition networks. For example, determinism. If I have a state in which I have several actions going off, several arcs going off that represent the same action trigger, then I have a non-deterministic automaton. that can be fine, right? It can be deliberate, in which I'm basically saying the application will decide, maybe randomly or because of some other thing that the user cannot control, which are to go down. But if it's accidental, then I've modeled actually more something like a production rule, right? It basically depends on random chance which of these two things fires in which order. Another thing that you can check is, for example, nested escapes, by which I mean, can I, I can check when I press escape to get out of one state and I press escape again to go out of that super state, I can nicely see how I plop out of the individual substates to get out of them. I can also check whether the same action, so the thing that's above a transition, always has a similar effect. Right? Am I always using, for example, the F2 key for things like completing an action or saving or exiting a dialog? Am I always using it consistently? So you can check that. You can even see modes, because every state that the system is in is essentially a mode, right? Because we said earlier on that modes are things in which the system can be in two different states, and I didn't use that word by accident back then, where the same action has different effects. That's a mode, right? Like VI. You enter, some letters, and if you're in insert mode, they get entered into the buffer. If you're in menu mode, they are interpreted as commands. And you can see these because these different states will literally be states in your state transition network. Okay, I want you guys to rack your brains for just a minute. This is a fairly easy one. I want you to draw a state transition network. So get out some paper and a pencil. And it's for this dialog that I've drawn here. So first of all, draw a state diagram that models the states that this dialog can be in if you only have a bold checkbox, okay? So ignore italics and underline for now. Imagine a dialog box that only has a bold checkbox. This is a very, very simple state diagram. Trust me, you've drawn this in like 10 seconds. Don't think about OK buttons or opening or closing this box or confirming choices. It's just what states can this dialog box be in while it's open when people are toggling this bold box on and off. Once you've drawn that, and that should really be easy, add an italics box checkbox to it. Okay, so then you have basically bold and italics as options. And people can, check or uncheck bold. They can check or uncheck italics. And if you're adventurous, then add the underline checkbox as a third option as well. So I would say draw 3 diagrams. The first one is just the bold. The second one is where you expand the bold with an italics option. And the third one could be the one where you have all 3. I'm going to leave you a few minutes to do this because this needs a little bit of thinking. And I want you to get a chance at least getting the first 2 drawn. I think then you'll see a pattern emerging. All right, so you've had a chance to rack your brains about this one a little. The first one is pretty easy, right? You probably found something like this. You've got your system is in a state where bold is not checked, and if the user clicks on the bold button, it will toggle the thing on or off, and it will move into the bold state. You maybe you've created this with 2 arrows. That's fine too, where you specify that when you go from regular to bold, you actually check off the box, and when you go back from bold to regular, remove the check mark. That would be even more detailed and precise, absolutely. But that's the overall thing. Now, you probably notice when you add italics, things get a little bit more complicated because you now actually don't just have 3 states as you might think, but you actually have 4 different states, right? You've got a state where both are off, up here, and you still have the existing thing to go from bold to non-bold up here, but you also have italics to turn on and off. And that is kind of adding a new dimension to your SDN if you want, right? We now have if you want a 2-dimensional SDN where the transitions that go vertical in my SDN here are the ones where I toggle italics on and off. Right? So from regular, I can go to a state where only italics is on, and I can go back to regular. But if I'm in the italic state, I can also press bold and then go to bold italics. And from there on, I can go back to only italics, or I can go back to only bold. Right? So the two things are basically, the x-axis now has toggling bold. The y-axis is toggling italics. And guess what? If you add underline, you get what you could call a cube, right? That we've tried to visualize here, where we have duplicated the whole the finite state machine once again, like we did before. We've duplicated what we have. So we move now from 4 to 8 states. And the front, if you want, and the back, if you look at it like a cube, 4 states are exactly the same, except for the fact that all the ones in the back here, if you look at it that way, are the ones where underline is off, and all the 4 in the front here, if you consider that the front, are the ones where underline is turned on. And we transition in that Z direction, if you want, by toggling the underline button. So I think it's easy to see what's going on here. We have an exponential growth of states, right? If I were to add another option like strike through here, then we would get, I always waited for the moment to say that we have a hypercube, right? We have a cube in 4 dimensions, right? So we've got one cube here, that's the left one on this size here. And in this case, we've added like capitalized. It doesn't really matter what you add. But here we've basically added another cube to this on the right-hand side, and all the states on the left are connected to all the states on the right. And you see the pattern. You're all smart computer science people, so you see what's going on here. So this is known as the issue of state explosion, right? If you combine 2 current SDNs, you get a new SDN that has, the factor of the product of the both numbers of states. And that means, what looked like a really simple dialog with these 3 checkboxes became a pretty messy SDN, right? And if there are 7 checkboxes, it's completely impossible to untangle in a drawn diagram. The more parallel things can happen, the more problematic this gets, and that's why GUIs are especially problematic in SDNs. But this is not the only case where this happens with GUIs, or with these multiple options and checkboxes in a box, in a dialog box. It also can happen to you when you have, for example, escape options or help options. Because if you hit escape, it basically means exit out of this subroutine. So for example, we had this issue that we had to complete the line drawing once we picked the line command as a menu option, and that of course sucks. So you could say, oh, anytime I hit the escape key, that will take me out of that tool and get me back to the main menu. That's great, but it means you now need to add a special second exit to every state in your line drawing dialog to get out of it, right? It's a new line. Similarly, let's assume you've got a help menu. You say, wherever you are, you can always press the help button, but it will actually take you to a help subsystem. But if you leave that help subsystem again, of course, you want to be back to where you were. You don't want to end up in a different state. And I'm not even talking about help systems that are specialized and showing you just contextual help. Even if it's just popping up a help screen and moving to this help state, somehow your system needs to remember that after it shows this help page, it goes back to the earlier one. And you see where this is going. If you're a computer scientist, we need to remember stuff. And that's what SDNs are not really good at. That's where we have then stacks, for example. So here are examples on how that could look, right? First of all, on the right-hand side, we've got the escape key. So every single state in here would actually have to have an extra exit with an escape key label on it, which means take me right back to the main menu state. We've simplified the drawing here by just attaching that to the sub dialog as a whole, but what that means is really it's attached to every single state. Similarly, for the help menu, if I press help in circle 1 and I leave the help system, I need to get back to circle 1, obviously. Whereas if I press it and while I'm at circle 2, I need to get back to circle 2. That gets messy. All of these things lead to state explosion. By the way, if we had instead had radio boxes in our dialog, right, picking only one option of the 3, super easy as an STM, right, because you only have 3 states, either option 1, 2, or 3 is selected. Maybe none of them in the beginning if that's an option for your design, but it doesn't explode, right? But Checkboxes are way trickier than radio buttons in this case, because they lead to this combinatorial explosion. And that's why everybody's favorite comes to the rescue, Petrinets. I'm sure you've all learned about and love Petrinets in your earlier computer science lectures. So they are actually, in our case, a pretty good approach to modeling dialogues that have several states at once, where basically the state of the system as a whole needs to be modeled as several aspects that need to be tracked and taken care of. It's not better for sequential dialogues or mutually exclusive UI elements like the radio buttons that I just mentioned. There it doesn't help you. In fact, it gets messier. But it's an established old model that basically models concurrency, right? So very quick primer here on Petrinets. I'm sure you guys know this all. The way we're doing this is a transition. These longish lines fires when all the input places, which are these round things here, have one or more token inside them. A token is produced in each output place when a transition fires. So tokens get magically consumed and new ones get generated. It's not like because 2 tokens get consumed by this transition that we only put 2 in the output. No, we consume all input tokens and fill all output places with tokens, right? That's how it works. And what you have to understand for UI modeling is that in a Petrinet, the current state of the network is not modeled by the one active state as we do in SDN, but actually by all the different tokens and the distribution of tokens throughout the network. In combination, they represent the current state. And that's where it's really different from state machines, much more powerful, more complex, but it can model things that we cannot model easily with state machines. So for example, if this transition here, if the user clicks, for example, this round flat thing is simulating a user action, like a user input. Let's say the user clicks. What would then happen is all these 3 tokens, the transition fires, the 3 tokens get consumed, they disappear, and the tokens appear in the output places, right? That's how we have to think about this. So if you were to imagine instead a Petrinet for our actual task with the preview, with the bold and italics button, it actually looks much easier because that will now lead to 2 very simple Petrinets. So this is the Petrinet for a, first of all, just the bold dialog. It looks very much like a state transition network because it's, there's not much going on yet. We don't use concurrency yet as long as we only have one option, right? For example, here, if the ellipse, that's where the user input can occur, and this ellipse basically represents the fact that the user presses bold. You have to understand that in Petrinets, these ellipses are the things that represent user actions. And don't think about these as states. For the moment, that model holds, but in the future, it will be facets of the state, aspects of the state. So this place up here represents the fact that bold is currently on, whereas the one down here represents that bold is currently off. We've got 2 transitions, and basically, what would happen is if the user presses bold, we get a new token in here, right? That means that the transition then fires because bold is currently on. There's a token, and the user presses bold. That means that both get consumed, they go away, and we instead place a token into all the output places, which is just the one bold off state. And since the user bold toggle action is connected to both of these, it works the same way in the other direction, right? It would place the token back up into the upper place if we were to toggle the bold button again. So far, so good. Not any easier than the state machine. But now it comes. If you add italics to it, it's super easy because you just duplicate this thing. But you don't duplicate the whole thing. If you were to add a third one, you wouldn't actually have to duplicate both of these. You would just add another one. So linear growth in the number of states as opposed to exponential growth. And that's the key thing. Now, if you add this, it works just the same as bold. We now actually have the state of our little dialog represented as the question, where does this token lie and where does this token lie? we see that currently the dialog is in the state bold is off and italics is off. But if the user were to press italic, only this token would wander up here, and then the state of the dialog as a whole would be bold off, italic on. So no more state explosion. All right. So that's the power of the Petrinets. They grow linearly with the amount of options that are parallelly available. But of course, as you can probably tell from just looking at these, they are also a little more difficult to grasp and understand, right? So that's the price you pay for this more powerful notation. And people have struggled with this and said, well, state transition networks are too lame, but Petrinets are too complex. Can we do something in between? And if you've taken any look at UML before, you know that state charts are a sort of in-between, right? State charts are used in UML, and were originally defined by Harel. And I'm showing you an example here of a simple TV control panel. We're going to talk through this in a second. In the way that state charts extend SDNs is, first of all, hierarchy. So we can see here, there's a standby state, that's the normal state, but the on state basically here is this whole box. That's the whole on state. So that's the hierarchy being in use. The second thing that state charts add are concurrent subnets, which is a little bit towards the power of Petrinets. We use this here in the TV example, where on the left-hand side, we are modeling the sound settings of the TV, which can be on or off with the mute button. And on the right-hand side, we model parallel to that the channel currently selected on the TV. This is a TV with only 4 channels, forgive me. But we can model actually these two things at the same time in parallel with the state chart. And what happens is when I enter this larger compound state here in this, both of these parallel substates, basically these subcharts, get resumed, they get started, right? So that's actually marked by these little black markers, which tell me that this is the state that I want this thing to be on when I enter this compound state. So every time the TV is turned on, the sound will be on, right? Because that black marker points to this, that resets this little machine. Whereas on the right-hand side, we have a starting marker, but it's marked with a history modifier. And that means if the TV was on and somebody selected channel 3, and then it gets turned off again, and we go turn it back on again the next day, channel 3 should actually be selected. It basically is a history buffer that remembers the last setting before that state was basically suspended. That's how it deals with multiple parallel sub-state machines basically running at the same time and being able to remember their state, a bit like the tokens in Petrinets, and then being reanimated, so to say, and revived in their last known state, if that's what you want, or you want them to reset to the same starting state every time. At the same time, we have here the exit. Anytime you press the off button while you're anywhere in the on state, where the on state is any combination of these two sub-state machines here, the off button will always take you back to the standby mode. And we can also see that there is a reset button on that TV, maybe a little over-designed, but it will make sure that the sound is on and that the channel is set back to 1. Right? That would be a reset version that doesn't restore the last selected channel. It doesn't make any difference for the sound option, but it does make a difference for the channel. So that's state charts, and you can see these are a little bit more powerful. The dotted line is important to remember for splitting substates that are basically available in parallel. And these enters, some things go into these state machines directly, and other things go to the outside of the state as a whole, meaning that they influence the state as a whole or trigger it or are available from anywhere in that substate. Lastly, let's assume we've done a good job at modeling our user interface as a diagram, or as in language form, whatever, any of these formal notations that you've learned now. We can also use this as a good starting point for documentation, similar to how we talked about this already with the GOMS model. This is especially true if your description uses screenshots, your state diagram to illustrate where we are, and if it is a bit more semi-formal. So like the one that we saw in the example of the China exhibit, is a really good one that you can actually use to, for example, teach a person how to use it. They wouldn't have to look at the state diagram right-hand columns, but the left-hand columns are extremely useful as a tutorial. Let me show you a very simple example of a digital watch here. This watch has two main modes, stopwatch and time display, and a limited interface with only 3 buttons on them. And button A is there to switch between time and stopwatch as a mode, right? So what that means is basically, if I press this button briefly, I get from time to stopwatch and back. If I hold it down for 2 seconds, I get to set the alarm. If I press it again, then I get to set the time. If I press it again, I'm back in normal display mode. Looks pretty good so far, right? What's missing? Well, if you look at this interface a little more in detail, you notice that some things aren't specified. Just like with the example of the graphical menu earlier. For example, what happens if the user presses A for 2 seconds while he's in the alarm setting mode? What does that do? Where do we go back? Do we go back to the time display or the stopwatch? And that's even true for the normal return here. We didn't specify in this drawing if once I'm done with setting the alarm and setting the time, if that takes me back to the time display or the stopwatch or the last one that was selected. We don't know, right? It's not specified. And so if I'm in the time, there's another question here. Let's assume I'm in time display. So my watch is showing the time. And I now press the stopwatch button for, I press button A for 2 seconds. What happens? Should it first go to the stopwatch, because that's what it said happens whenever you press button A, and then after 2 seconds, move from stopwatch into the time setting, the alarm setting, sorry? Or should it directly go there after 2 seconds and only enter stopwatch when I let go of the button? As you can see, we're missing something here. To really be precise about how the stopwatch should work, we need to specify what happens not just with single button presses as we do here. We need to talk about what happens when I press this button and when I release it. So push and release, right? So lots of questions here. There are dangerous states. There's questions of completeness that we've seen here. We need to distinguish between depressing button A and releasing A. We need to talk about what all of those actually do in all of the modes to be a little bit more precise. So here's a better model of the stopwatch. The whole top thing here is the normal mode where I'm not setting anything on it. And I've now specified that when I'm in time display mode, and I press the A button once, I hold it down. The moment I push it down, I immediately want to see the stopwatch. If I then release, I want to still see the stopwatch. If, however, I hold it and 2 seconds expire while I'm depressing A, here I'm depressing A in this state, I want to move then from the stopwatch to the alarm setting. If I then let go, I stay in alarm setting. And I need to let go to get out of it, because the only way to exit is to press A again, and I can only press it again if I have let go, if I have let go of the button before. So then I immediately enter, when pressing it, the time setting mode, and I stay there, and I need to release and depress again to get out of it, and that will always take me, as I'm showing here now, to the time display. So I'm never going to go back to stopwatch. I'm always going to go back to time display. So this is a little bit more specific. It removes some of the ambiguities of the earlier version of our simple sort of naive approach to modeling a stopwatch. But you can see it gets tricky, right? And it's not that this is like useless work to just go through the the footwork of the legwork of doing all these different specifications. It actually contains important design decisions that in the end determine usability. Some of the decisions that you make there will make the system easier to use or more annoying to use, and so you have to put some thought into it. And it's just one button, right? We've just talked about a stopwatch with one button and basically just a few modes. Imagine how difficult this gets with a more complex stopwatch or a multi-function alarm watch or any kind of modern device that has more than 3, 4, 5 buttons in different modes. So this is not easy, but you can be very specific, but it is not an easy task to do. So the complexity of designing the interface well doesn't go away, but at least you now have a language to express your design precisely if you choose to. We mentioned early on that the semantics aren't captured well in many of our representations, right? And that is especially true for raw code, because some people say, well, if I read the source code, I see how the interface is working, right? But if you look at this selection here, can anybody tell me what this code is doing? Yeah, Hannah, go ahead.
I think I would need to look up all the different functions because I really don't know what they're doing. So the code itself doesn't really tell me much.
Mm-hmm. Yeah, that's true. So you're absolutely right. We are not actually seeing the semantics of what's going on. The only way we can guess at the semantics is by through the naming of these different functions, right? So is anybody willing to take a stab at what this is doing? Jasper?
Yeah, so I guess, yeah, EV stands for event. So yeah, event type is quite clear, okay, and then pos maybe will be for position. And in text would be, I guess, input text. But yeah, it's pretty much guessing.
Yeah. So input text, not quite, but Victor, you want to take a stab at guessing what this code does or what it was written to do?
Yeah, I think this if in text, like if we select a position inside the text, so then we set our mode to selecting, and we start a function from this position, the selection starts.
Right. So if you look at it as a whole, this is basically describing the code fragments to select text in a word processor. Right? If I push my mouse button down, like that's the first event type, and I'm currently within a text block, then I set a set a variable called mode to select to be in selecting state, and I mark the beginning of the selection. Right? I remember visually I highlight that's marked. I remember the position and so on. And then if the mouse gets moved, let's maybe look at that first. And I'm in this mode where I'm currently selecting, then I extend the selection over the things that are being moved over. But that's only the case if I'm still in the selecting mode. And if the button goes up, I set the mode back to more normal if I was currently in the mode selecting and I'm still inside the text. And I say, okay, that's the end of the selection. So in a way, this is basically selecting text or something like that in a word processor. But you see that the trade-off is terrible, right? We have a lot of text, we have a lot of things to read. None of you looked at this and said at a glance, oh, I know what this is. So raw code is not a good format for capturing user interface behavior well, right? So the description of the dialogue is very distributed on this, and it's basically not a good way to describe text. So that's why we learned these other ways of visualizing or expressing the structure of dialogues and of interfaces in general. All right, so we're kind of done. First of all, for this particular section here, the Dix book and also the Schneiderman book are great resources if you want to learn more about these topics. I recommend them. And a lot of the material that we talked about today in particular can be found in Alan Dix's book, so that may help you if there was something that seemed not clear to you. Which takes us to the end of this class. So what did we do? We looked, it's a class in human-computer interaction, and I tried to take you through, first of all, some aspects of human psychology, things that you can remember until the day you die, because we're not going to get brain upgrades anytime soon. And many of these factors will stick around and will be true no matter how technology changes, because people don't change that quick. We talked about human performance, affordances, mappings, constraints, blah, blah, blah. All these things that we'll learn from Norman's book. We had the basic CMN model and those kinds of things. And we had a quick session on visual design, and I recommend going back to those things. For example, visual design will help you a lot if you're creating your next PowerPoint slides for your next presentation, and pay attention to some of those things in there. Case studies was the second part. This was a bit weird, maybe. It's like, why am I learning about people from the 50s, pressing buttons on a computer? The point was that we really only can understand where a field is going if we have some kind of sense of trajectory. And that requires you to know points in the past as well as in the present to see where we're going, and not to repeat the same mistakes again that people have made before. Also, I wanted to show you how visions often sometimes become true, but oftentimes look completely off the mark, and how reality often develops very differently. So when today you see the next vision of how the interface of the future is going to work, everybody's going to wear head-mounted glasses, take those things with a grain of salt and be aware that reality will often kick around those visions quite frantically and turn out completely differently. And then finally, I think understanding that there is a long phase from when an idea first pops up in the research labs around the world where people are developing new interaction techniques and technologies to the point where it actually ends up in a product. In the past, this has often taken as much as 30 years, right? Like the first touch screen, for example. So be aware that the best way to predict what's going to happen in the future is to really stay up to speed on research results. Even if you end up doing a job in industry later, stay focused on and keep an eye out on what are the cool things being presented at the research conferences of the day, CHI, WIST, for example, to understand where the industry might be heading in the next couple of years. And finally, we took a long turn through going through the development process, teaching you the ropes of how do you design and evaluate and implement prototypes with users, without users, and how do you get to great software products and software hardware products by going through these DIA cycle iterations. So what's next? First of all, in the summer, there is Designing Interactive Systems 2. This is a class that talks about what makes a user interface tick and more about the technical concepts, the software paradigms, the technologies behind HCI and user interface development. So this will be a class that, for the computer science minded of you, this will feel more at home. There's more programming, more technology, more software architecture talk. I enjoyed this class a lot because you get to build your own event-based Windows system, and you get to play with a whole lot of different toolkits from mobile and desktop and post-desktop, Arduino, embedded microcontrollers, all kinds of things to learn how these things work technically. So DIS1 was kind of like the brainwashing for knowing how interfaces should work and what the end vision should be. And now we're going to get to how are you going to be able to implement them. And then there's this class, Current Topics in HCI, in the summer, that is about understanding and practicing ways to do research. So on the one hand, it's a really good class if you want to prepare yourself for writing a thesis at our lab. In general, you will be learning the scientific methods of running controlled experiments and creating validated scientific results, which is the status quo in not just HCI, but academic research pretty much everywhere. And then it has a set of talks by our PhD students in which they each talk about one sub area of HCI that is currently hot and that we have a particular interest in. Maybe because we're doing work in this ourselves, or maybe just because we really like the field, where we're filtering basically a little bit by our own interest, but it gives you a new idea on what is currently happening in this field of HCI and what are some things that you might get involved in your own thesis. It's also a great class to take part in because it basically is like a little bit of a catwalk of all our PhD students. So you get them to presenting their own work and talking about what they do, what they enjoy. And so you can see whether there's somebody there where the topic and the person is somebody and the topic is something that you want to hook up with. All right, these classes in the upcoming semester, I have a research semester, a Forschungssemester. So normally these classes wouldn't take place, but we decided to offer them still as a way that you can actually gain credit on them, so that you guys aren't slowed down in your studies if you choose to, if you find these topics exciting and want to do them. But it will be offered in a self-study format. So you will basically be able to get access to all the materials. We've got the talks online, we've got the slides, we have assignments that you guys can work on, but we will not be offering the usual sort of graded, reviewed assignment, individual feedback on each week. We will be, and there will be no midterm, but we will be offering regular times where you can check in with assistants if you have particular questions about the material. And there will be a final exam that you can write in order to get the credit for this class. So it's sort of a stand-in solution so that you don't just have to wait for a whole year to take this class. It won't be quite as interactive as we normally do our teaching, but the option would have been to have no teaching at all, and I figured that's probably not a good idea. Our seminar and practicum, like practical lab, are actually also happening. Simon Völker, postdoc at my lab for quite a few years, is taking over these classes. So you're already signed up if you are interested in these, so you know that these are taking place. I'd like to thank you guys all for participating and being part of this class. And I hope the brainwashing wasn't too intense, but I hope some of it sticks around and you will become sort of nitpickers that will complain about bad user interfaces a lot. But hopefully also appreciate good UI design when you see it and maybe help make technology a little bit more usable through the things and tools and knowledge that we've sort of pushed at you this semester. Thanks to Ollie for supporting us here, and also Marcel for running the lab sessions with Ollie. And good luck in your further studies, and I hope to see you guys in our upcoming classes.
This content was provided by RWTH Aachen University.